The topic for this video is going to be modularity. We want to break down the code that we have in our application into multiple files, and we want to make it easy to separate a bunch of functions that we anticipate we're going to be able to reuse in a multitude of projects. We want to make it easy to separate them into their own file, so that then we may actually include those files in other projects. And the word include is important here because we are going to use the pound include directive, pre-compilation directive there. So it's going to shed some light as well as we build our modular application. It's going to shed some light on how the standard C library is also organized itself. So let's jump into the code. We have our hello world here. So nothing new here, nothing exciting, except that the hello world is not located where I thought it was located. So let me fix that right away. Let's see. And a little bit of command line here on the way. I'm going to go to the editor and I'm going to reopen and go gedit, oops, gedit main.c. I don't think I need to background it. No, I don't. All right, there we go. Close without saving. All right, so I'm going to modify this to make sure I'm editing the correct version here. gcc main.c and then a.out. Hello world, perfect. So what we have done in previous videos, we have broken down this into several functions, okay? So I'm going to do this real quick here. I'm going to extract that hello world, and I'm going to say display greetings. We're going to make a simplified version of what we have done in previous video. So I had my header, I had my prototype for the function before the main, okay? So void display greetings. Okay, and I add the definition of the function after the main. And this function, of course, is going to do only something trivial. There we go. All right, save that. We didn't change anything really. We just refactored the code so that it's organized a little bit differently. Now I want to get to the interesting part. The interesting part for this video is what if that display greetings function that I wrote, what if it was something highly reusable, something like, you know, the square root or the elevation of a number to the power of an exponent, something that I anticipate I'm going to be willing to incorporate into many projects in the future. I could give this source code to this main.c file, you know, to whatever programmer wants to reuse, you know, my function. But then my function would be probably in the middle of all the code for my application, specific to my application. They would have to look through it, they would have to find the definition, and they would end up cutting and pasting inside their own code. So we would have different cut and paste version of this function everywhere. Well, that doesn't sound like a big deal, right? Except the day that I decide that I'm going to upgrade my display grading and do something fantastic, such as, for example, removing that \n. I would like every version of this function to actually benefit from this modification. And if everybody has been doing cut and paste, what am I going to do? Send a bunch of emails to those programmers, let them know, hey, by the way, I changed my code, so you might want to check, you know, your cut and pasted code in all of your projects, etc. No, we want to be able to exchange like a file that contains just display greetings, and that is going to be what I'm editing, when I'm modifying, improving, or fixing bugs in my code, and then I can exchange that file, I can send that file, and people can integrate it into their project, and they don't have to even modify that file. So that's the idea being that when I release a new version of the file, they just take the new version, drop it in place where the old version was, and it's good to go. Okay, you can see how this will make the sharing of code and the reuse of code a lot more a lot easier, pretty much. Okay, so we are going to do exactly that here. I want to take this, okay, and I want to put it into its own file. So right now I have a file called main.c. Well, let's do a file called greetings.c, and I'm going to greetings.c, and I'm going to put inside greeting.c the definition of the method display greeting. There we go. Okay, so my display greetings here has just been moved to another file. Nothing really like tremendous there. Okay, I'm going to save that file. How can I compile now? Well, if I compile now, my application needs more than one file. So I would have to do gcc main.c and then greetings.c. Let's try. So if I try to do this, it tells me inside greetings.c, in the function display greetings, implicit declaration of function printf. So if I move this function here to another file, and this function uses other functions that are defined elsewhere, I still need to do the same thing I was doing in my main.c, which is include, in this case, stdio.h. So let's do a quick cut and paste of #include stdio.h. So this is important because that means that there can be a chain of dependency, right? For example, I could have the greetings file include some information about stdio.h. So there's somewhere there is an stdio.c that implement actually all the function which headers are in stdio.h, and then that stdio.c could depend on stdlib, for example, and so on and so forth, right? So there is this idea that we might end up with a sort of graph of dependency, right, between our file, our little modules. So for now, the dependency is pretty easy. So I just need stdio. Let's try to see if that's enough to make the compiler happy. Yes, it is. What if I try to run this? A.out, it'll work. Okay, it's working. Let's try to make things a little bit more standard. Here, I have the prototype of display greeting. What would happen if I remove it? Well, let's see. Let's try to compile this. Implicit declaration of function display greeting. So now that all those implicit declaration messages should start becoming familiar to you, that means that when the compiler is compiling the main.c file, it processes all of this. Then it finds display greetings. It never heard of display greetings before. Even if it compiled that file first, it considers the files as being separate entity. So it compiles that one compiles, but then it compiles that one, and it says display greetings, never heard of it in this file. So we still need we need to put before the main the prototype of the function display greeting. And I said include because, yeah, we are going to do an include here. What we're going to do is we're going to say, you know what, this prototype, I don't want to have to cut and paste it for the same reason than before. I don't want to do like cut and paste oriented programming. So what I'm going to do instead is I'm going to include greetings.h. And if I put those chevrons here, those angular brackets, that means that the file greetings.h would have to be found in one of the standard locations on the disk where all of the standard C library header files are found. Well, mine, I'm going to write it here. I'm just going to create it here in this folder. So I have to specify its name between double quotes. Okay? Very important distinction. So when I say #include greetings.h double quote, it's going to look in the current working directory right here for a greetings.h file. And of course, I don't have a greetings.h file yet. So I'm going to create it. There we go. And inside that greetings.h file, I'm going to put my function prototype and save. So let's sum up. I have a main.c. The main.c could be my application. It does a lot of stuff, 5,000 lines of code, whatever you want to imagine here. I call a function display greetings. That function has been given to me, for example, by another programmer who shared with me the greetings.c file that contains the implementation of the function, so the definition, and a greetings.h file which contains its prototype. To be able to use display greeting, I include greetings.h in the files where I'm going to use that function here. And when I compile, I make sure that I compile with both C files. so that they are going to be put together, and then when we assemble the executable file, the linker is going to be able to find actually the code for the function, which is going to be from the compiled version of greetings.c. Okay? All right, so I just recompiled it. Okay, it seems to be working. A.out to test it out. Hello world, still working. Okay. All right, so we have like a sort of pattern here. We have a sort of recipe. Every time you want to write functions that you anticipate you are going to use in different projects, you put them in their own C file. That C file needs to have all of the include that are necessary for your functions to do their job. And then you create a H file that has a header of the function you want other programmers to be able to use from your file. And when you want, wherever you want to use this function, you include the header and make sure that you compile alongside your application file with the greetings file, which is kind of our module, our library, if we want to call it that way. It's not really a real library, but it's kind of the intent, of putting reusable code into a unit of code. And that's it, and that's the recipe. So there is one thing I need to warn you about. I'd mentioned sooner that when we have this dependency, our file depends on stdio maybe depend on stdlib. Well, that means that all of those C files are going to do their own pound include. Is it possible that, for example, my file here include stdio.h, and one of the files, the headers that I include here, also include std h.h. Yes, it's possible. Would that be a problem? It is a problem. In the header files, you can display things, declare things like functions. You can also declare constants. You can declare variable. For example, here's a constant, double. I'm just going to do pi because why not? So 314, 15. Okay. Oops. Cannot type today. All right. Or I could have what we call a global variable. Okay, a global variable. When you have only one file, a global variable would be declared and defined here. For example, int global age equal 42. Okay, and that means that this variable is usable inside the file main.c in any function that you define there. So for example, inside the main, I could say something like global age equal a different value, or if I have another function here, okay, inside that other function, I could definitely do things such as global age plus plus, increment global age, right, and then printf the new global age value is, and we are going to insert a %s. There we go. And I'm going to put global age. There we go. So we have the concept of global variable, okay, which can be accessed anywhere from any function in a file. Let's compile this. Let's call another function from the main so that it executes and does something with global age. Another function. And let's run this. So what does it complain about? Implicit declaration of function, another function, no problem. That just means the header. So here I'm going to take this and I'm going to put the header of that function as a prototype right here. So I can have a mix, okay? That's the first thing that comes out of this. I can have a mix of functions that come from other files and functions that are just defined regularly in the same file. No problem at all. And we learned to do both. So now we should be all set. So I'm going to save that and let's see what else we need to fix. Another function format %s is expected for string. Well, that's not an interesting bug. Okay, that's just me putting %s instead of %d here. So we are going to fix that one, and there's not much to say, or at least not much interesting to say about that. Okay, I run hello world. The new global age value is 43. Awesome. Of course, if I keep running it, it's going to have the same exact behavior. So every time I start this code, the global age variable is available globally inside main.c. And it's actually set to 42 every time I start. If I call another function several times, what do you think is going to happen? Am I going to get 43, then 43 again, then 43 again, or something different? Well, let's check it out. GCC, a.out. 43 the first time, then 44, 45, 46. Well, yeah, the global variable exists. It's kind of like it exists outside every function. So we have been talking about the scope of a variable, right? When you declare a variable inside a pair of curly braces, it exists only in that block. When you declare it inside of a function, that means only when the function is called, that variable is going to be created and is going to be used, and then it's discarded when the function exists. Well, here we are outside of any function. That means global variable. That means the moment the program comes into existence, starts executing, we are going to have global age available and set to 42. So if I keep using it from a function and I call that function several times, every time I increment by one global age, I increment it right here in that variable, right? So it's kind of like a global counter. Well, this is awesome. I don't need parameters anymore, right? Wrong. Absolutely wrong. Very, very, very dangerously wrong. As a matter of fact, you should not use global variable unless you are asked specifically to do so. Okay, that tends to break completely the modularity of your code. Now suddenly we have this thing that is accessible by every bit of function in the file, and we're going to do even worse than that. We're going to make it accessible throughout the entire project. Anybody can just modify it at some point, and if they make a mistake, then tracking down that mistake is really, really difficult. So no, global variables are not a substitute for proper writing of function with their parameters and their return value. Okay, they are just something that sometimes we need to use, and they are available. But for the scope of this class, of this course, I will let you know when I want you to use global variable. Okay, sounds like a deal. All right. So we have this global variable. What does this have to do with, the header file? What does this have to do with the C file and stuff like that? Well, let's work our way to that. I'm going to go here first into display greetings, and I'm going to say, you know what? I would like to say hello world, and between parentheses, the value of global. What did I call it already? Global age. I guess I was thinking about the previous, you know what, let's call it just global, because I was thinking about the previous code that we developed where we had like the age and the name for the greeting, but we are not going to go in that direction. So we might as well, just rename it something a little bit more neutral. So what I'm trying to say now is that when I display hello world here, I want to access the value of the global variable named global. All right. Global age undeclared, no problem. That's me forgetting to, line 23, that's me forgetting to actually use global. Yeah, there we go. There it is. I was focused on line 22 instead of 23. Save that. All right, compile. Global is undeclared. That one is more interesting. Where does that happen? Greetings.c. Greetings.c uses a variable global. That variable is not a parameter of the function where the printf appears. It's not a local variable declared with scope inside that function either. It's not a global variable in that file. So where does it come from? The over file. Well, when you have a variable like that comes from an over file, you need to do kind of the equivalent of a prototype. You need to declare that variable. So I could do something like, and I'm going to use a new keyword, extern int global. And I don't assign a value, okay? Extern means, well, first, this is a global variable that I'm declaring here in the file greeting, but extern means, hey, this is just a declaration. The actual definition of the variable and potentially its assignment to an initial value is done elsewhere in another file. That's what extern means. And it's kind of intuitive, right? You are in a file, greetings.c, you say extern int global. Okay, so there's going to be an int global defined somewhere else in one of the other files of my application, okay? So it's kind of like the prototype, the function prototype. I'm going to save this. I'm going to compile. I'm going to run. There we go. Now it's working. So we have found a way to make global variable. We have found a way to make global variable. So the first version was available inside a file to all the functions inside a file. Now we can make them available across all the files that make our application. So what would happen if I did, for example, in greetings, what would happen if instead of declaring global right here, okay, I made its declaration actually appear in greetings.c. So instead of global being defined in main.c, is defined in greetings.c, okay? So I switch things a little bit around, but I still want to be able to access it from both files. And then I could go here and I could go in my header file for greetings.h and say, well, everybody who is going to do a pound include of greetings.h is going to know that there is somewhere else a function display greetings, know that there is a constant pi, and know that there is an extern int global. So that means that somewhere else, in this case greetings.c, I declared a global variable. So if I want to give another programmer a module that contains, for example, one global variable and one method that I want them to be able to access, this is how I would do it. Define everything in the .c file, greetings.c, declare everything in the greetings.h, then allow main.c, and I don't need to redefine pi here, that was just an example, okay? And then allow whatever file from whoever in the team, whatever other programmer, to just do an include greetings.h, okay, to get access to both my global variables and actually my functions. Well, let's see if that works. GCC seems to compile. A.out. Well, it's working, right? So we have a way now, we have a neat little way to encapsulate, a bunch of functions. And if those functions need to share global variable, we can encapsulate those global variables there as well. We encapsulate all of that in a C file. We write a C file. Then we provide a H file, a header file, to allow people to include that header file so that they have the declaration of everything I want them to be able to access. And then, just by including that and compiling alongside my C file, they get access to everything in my little quote-unquote module, okay? And that's really similar to what's happening here, okay? It's really similar to what's happening here, except that when I include stdio.h, so because of those angular brackets, that means stdio.h is located elsewhere, okay, in a standard location on your drive where all the header files for the standard C library are located. But it means also that when I compile, I need to compile with the source of stdio. Of the source of the module stdio. And I don't have them. So what happened? Well, it's just automatic. If you include a standard library like stdio.h, right, when you compile, you're going to be linked to that library. Some of the libraries, like for example, what was it? The math library require you to add a -lm option to your compiler. Okay, so that means that, hey, by default, their code is not integrated with my executable, -lm, go and find their code, integrate it. So what does that mean, go and find their code? Well, it means a compiled version of the code. I don't even need to see the source code, okay? I could actually give to someone a .h, greetings.h, and instead of sharing with them my code, greetings.c, I could give them the compiled version of my code as a file, greetings.o. Okay, this is greetings.o is a compiled version of a source file like greetings.c. So if I give you just the header file, you can include it. So you can start writing code using my methods, my functions, and my global variables. And then when it comes time to compile everything together and link together your executable, you are going to have my .o file, so you have the compiled version. So I can even share with you some code without necessarily sharing the source file. Okay, and this is kind of like the basis for library frameworks and stuff like that. So we're not going to go much further in this, but the one thing I'm going to add to kind of close this topic is What if the greetings.h file end up being included several times? Okay, in several files. Like for example, one file includes the greetings.h, but then that file is also included from another file, and that file originally also included greetings.h. So now we find ourselves including twice greetings.h. Okay, let me show you on a little diagram quickly what I mean here, because it's a lot clearer visually than it is just explaining, audio. So let's say that I have here like a main, oops, main.c, okay? This is my main file, and I'm going to have a bunch of pound includes in there. So one of the pound include, I should have made my box a little bit bigger, right? One of the pound include I'm going to do is pound include, let's say, greetings. I apologize for the abysmal handwriting. This is why I use slides and I type code instead. Greetings.h, okay? So that means that pound include greetings.h, that means that somewhere there is a .h file, okay, and that .h file is called greetings.h, okay? And there is also a .c file that contains all the definition. Here we are, greetings.c. Okay, and what I'm doing here when I do a pound include, I just take everything that is in that file and replace that line pound include greetings.h by the contents of all of this file. And what if inside this file there is also a pound include? Okay, nothing prevents us from saying, for example, I want to include something from a file called let's be super original, f2.h, file number 2.h. Okay, so what happens when I do include? Well, it's the same thing that happens in the main. And include means that there is somewhere else, a header file called f2.h, right? There is probably a f2.c somewhere there hanging around, which contains a definition of everything that's declared in f2.h. Saying pound include f2.h just means that you take the contents of this entire file and you insert it here to replace the line that says pound include. Okay, it's kind of like a cut and paste, right? Nothing really like super fancy. This is what the preprocessor does. Well, what's happening here? What if, so we have greetings.h including f2.h. Okay, what if I want to, so that means that greetings.c is probably using some of the functions we declared here, a global variable. But what if I want to use those functions also independently in main.c? I could say pound include, okay, f2.c. And if I do this, same logic, right? Everything in the file f2.h, sorry, not c, there we go. f2.h is going to be cut and pasted here to replace that pound include line. So here's the interesting bit though. Now I find myself with whatever I have here, I'm going to put it in red, okay? Whatever declarations I have here, like global variable or whatever, right? I'm going to include them right here. So this is going to be replaced by all those declarations. And then when I include greetings.h, I'm going to end up with including everything that's in greeting.h, including this. This is going to replace that one line here. Okay, so that one line here is going to be all of this. And then what? And then when I include f2.h again, I am going to once again include those definitions that come from here. Okay, so they are going to appear twice in my main.c. Sometimes it doesn't matter. Sometimes it matters, like when you are declaring a constant, declaring a global variable or something like that. Then are you trying to define them multiple times? As long as you do extern, you're okay. If you are trying to do like the definition of the variable, there's going to be a problem. Even if you try to reference twice, extern this and extern this twice in a row in a file, the compiler, I think, is going to yell at you for that. I'd have to double check. I didn't do that in a while, but the compiler is most likely going to yell at you. So we want to prevent those kind of problems. We want to prevent the problems where we have multiple inclusions of the same .h file, header file data. So here's how it works, how we can do that. Let me start by the easy one. Pound pragma once. At the beginning of a header file, you say hashtag pragma once, pound pragma once, okay? It doesn't look like it's going to do a lot. My program still works the same way. But if I was to, from other files, if I was to directly or indirectly pound include multiple times, this greetings.h file, that would be okay. Like, okay, for example, here, let's take a stupid example. If I just did something like this, okay, that would be just fine, because the pragma once directive is there to say make sure that this header file is only included one time. Okay. Pragma once is, I don't remember if it's been defined in C99 standard or C11 standard, so it's been defined a little bit ago, right? But it's still relatively recent. We didn't have that at the beginning of the C language, for example. So when we didn't have that, what did we end up doing instead to protect our files from multiple inclusion? Well, we were using over precompilation directive, but a little bit more complicated. We're using this formula here. If and if, which is kind of an if statement, but for the precompiler, right? And it says if something is not defined, something has not been defined. So if and if, and then we use the name that started with generally underscore, and that would be the name of the file, okay? The complete name of the file with an underscore at the end as well, okay? And actually, most of the time, we even put an underscore here. So the idea was we are going to say if nobody defined a symbol, and I'm going to explain what defining a symbol means, okay, for the precompiler. If nobody defined a symbol named greetings.h, so that symbol is unique, is a unique name based on the unique name of the file that we are talking about here, right? Then I'm going to define it. So that's what defining a symbol in the precompiler looks like. That's what it looks like. Pound defined, and then the name of the symbol. So it's kind of like a binary field thing. A symbol is just a name for the precompiler. When you run pound define and the name, then the compiler takes note that that particular symbol, that particular string, has been defined. Okay, and it just makes note of that somewhere. And then when we use if def or if and def, okay, there's two variants of that if statement. One that check if something has not been defined yet, and one that checks if something has been defined already, okay. When we do this, well, we just look up if we encountered a pound defined before. So here we're saying if greetings h symbol has not been defined yet, define it. And then we put our code, and then at the end, and if. Okay, so this is the end of the if and def at the beginning. What are we doing here? What are we playing at? So let me illustrate this again. So first, let me compile it to show you that it's indeed compiling. There we go, compiling, running, no problem. Let's go back to our whiteboard here, and let's try to illustrate a little bit what's happening. So the idea here is that we want to prevent multiple inclusion of the same declaration that are present in a header file, okay? So let's first illustrate a scenario like this one. Let's say I have main.c. Let me switch color real quick here. All right. I have main.c. And I'm going to do something stupid. I'm going to do a pound include of, I'm going to call it just something dot h, okay, and then I'm going to do again a pound include of something dot h, okay. So let's put that in a nice little box. Somewhere else, I have something.h. And let's say that that file contains, I'm going to indicate it as a box, a red box like that. Some declarations of global variable, whatever you need, okay? And then, of course, somewhere else there is something.c, but we're not going to be too worried about something.c in this example, okay? It's there, it's doing its job, fine, perfect. So what happens when I include something.h? Well, this line here is going to be replaced by the code that is inside the file something.h. What happens when I pan include something.h again? Again, this line is going to be replaced by the code that is coming from something.h. When I am done including all the files like that, all the header files that I need to include, I compile main.c and I realize that I have code here that duplicates code there, and depending on what the code is, that can cause some serious problem at compilation level, okay, like trying to redefine a function, trying to redefine a variable, and so on and so forth. So what am I going to do to avoid this? I use that if and def thing, right? So here, this is going to be a little bit small, so I'm just going to mark it with a hashtag, okay? I have my if and def something.h, then define something.h, then end if here. Well, those are part of the header file, so those are going to be integrated when I do the include, right? So there's going to be a if and def, and then the name something, blah, blah, blah. Then there is going to be a pound define, the same symbol name, something, blah, blah, blah. And then there's going to be end if at the end. And then same thing here, okay? If and def, then define, same symbol name, okay, something h with underscores, and then end if at the end, okay? So what's going on here? Well, now that I included all of this, okay, twice, as part of the inclusion process, the preprocessor is going to also execute pretty much those directives like pound, if, and def, etc. How is that going to work? First, if not defined, this symbol here. Well, this is the first time I see that symbol, so no, it's not defined true. So that means that I'm going to let everything between the if and def and the end if here, all of this is going to be included in my file main.c. Well, the first thing that I do is pound define the symbol. So now it's been defined, and then I integrate the code that is defined here. So that all happened when I resolve, when I process the pound include statement, this first one here, right there, okay? So we have conditional inclusion of code. We don't simply grab pound include a header file and take all the content of the header file and put it in our C file. We take all the content, but that content is also featuring pre-compilation conditional directive like if def, if and def. So I execute those two, and those allow me to say, yes, go ahead and include that content, but I'm going to make a note that I define the symbol something underscore h. So later on, if I'm asking myself pretty much, did I already include this content in this file? I'll be able to recall it because I defined the symbol. And that's exactly what happens here. Once I'm done processing the first pound include, I process the second one. I take everything that's in there, put it here. That includes the pound if and def symbol, the same symbol that I defined. So this time the conditional is false. Okay, because if not defined the symbol, well, yeah, I just defined it here. I remember. So this is false. That means that everything between the pound if and def and the end if is not actually included. So that's it. We did conditional inclusion of the content of a file, and to keep track of whether we already included that file or not, we use that little pound define here with a special symbol, and that special symbol always has the name of the file with underscore like this, so that it's unique to that file. It really corresponds to that file. Yes, pound pragma once is easier, but I wanted you to also have this because you are going to encounter this pattern a lot if you look at old C code, legacy C code, okay, because this is how it was done before the introduction to pragma of pragma once, and pragma once was introduced in around 99 or 2011, so it's relatively recent, okay. So with that, we have all the recipes that we need to be able to actually create little modules. We know how to declare and define functions. We know how to declare and define global variable if we need them. But again, in the context of this course, I will tell you when you need to use those in your projects or in your exams. So we know how to define those things. We know how to declare those things. We know we put the definition in the C file. We know we put the declarations in the header file. We know how to protect that header file from multiple inclusion. The last thing that I'm going to discuss here is actually how do I make functions or global variables in my greetings.c file that I don't want other programmers to be able to access. So I want to share with them a part of my code, right? But I want to hide another part of the code. So in object-oriented terms, this is called encapsulation. Okay, abstraction encapsulation is the idea of hiding code like this and encapsulating it into a module, pretty much, called a class. Here we don't have classes, but we have a few mechanisms that allow us to reap some of the benefits of object-oriented programming. So here in this example, let's say I have a global variable global, and I have a global variable secret, and this is whatever secret number that I don't want the code from other programmers, like for example the main.c, to be able to access. And then I have here this little variable, this little function, that I'm going to call void do something, and it's going to be called inside here. Okay. And while I'm okay with you calling directly display greetings, I never ever want you to call do something by yourself, okay? And all it's going to do is, for example, increment the secret value. All right. So I want other programmers, when they include my greetings.h, I want them to be able to use this and this. I don't want them to be able to use this and that. So the first thing I'm going to do is I'm going to make sure that in the greetings.h, I don't mention everything that I want to hide in my implementation, okay? Not everything in my implementation should be visible. For example, if in order for me to do display greetings, I need 47 global variables and 253 different helper functions, right? From your perspective, the person using my module, all you care about is that when you call display greetings, it does its job. The fact that it was a complicated task that took so much work on my side should not be something that you have to constantly keep in your mind, keep in your memory, and worry about, right? That's the idea of abstraction in programming. You give me a job to do, I'm going to write like 5,000 lines of code in that greetings.c file, okay? But the only thing that's useful for you out of that file, the only role of that file, is to expose the display greetings function to you so that you may use it. So that's fine. I'm going to make some things visible to you, and you can use them, and I'm going to hide the little details that allow me to make this work happen, okay, that you should not worry about. So that's the first step. The first step is the header file should not have declaration for anything that you don't want the main to be able to access. So for example, here, I have that variable secret, right? So if I was trying to do something like printf %d, and I'm going to put on a row that says secret. I'm trying to access that secret global variable, right? So if I save this, go back here, compile, there we go. So warning, %d expects that I give actually a variable. That's not interesting, it's just something I forgot to do. So there we go, secret, variable secret. Let's try again. secret undeclared. Now that's interesting. Okay, that one is more interesting. So secret here is not visible. Why isn't it visible? Because the only way for me to view things from greetings.c is by including greetings.h. Okay, greetings.h does not mention secret, so we are done. That's it. I cannot access it. The next error is less interesting. It's just that do something here. That do something needs a prototype. Okay, but I'm not going to put it in the .h file because I don't want it to be exposed. I don't want people to be able to call the method do something. So I'm going to put my prototype inside greetings.c, sorry, but I'm not going to put it inside greetings.h. So okay, now I'm left with that interesting error here that I cannot access secret. And if I was trying to call do something here, let's see what happens. Compile. Well, the do something would actually be I don't want to say allowed because really you should not be doing that, but I'm kind of stretching here what we can do and what we cannot do. The do something here that I tried to call is just that I'm trying to actually trigger that method. There we go, something without it being exposed. So now that I have it back here, let's try again. And implicit declaration of function do something, so that means I need a prototype. Okay, so where is my prototype? It should be in greetings.h. It's not there for a good reason. I don't want it to be exposed. So here's the first layer. Okay, the first layer is in your .c file, there are things that you want people meaning other programmers, to be able to use and access. Okay, there are things you want to keep to yourself. The ones that you want other programmers to access, you put them in the H file. The others, you don't mention them in the H file. You don't declare them in the H file. When I include, that's going to be a first level of protection. Now let's play sneaky. What if I do something like void do something? Okay, we're going to try to see if we can break that protection layer that's in place. Okay, what if I put a prototype here? Because I read your code, I had access to your code, I read your code, I see that you have a do something method. I'm interested in calling it. I want to call that method, okay? So it's not in the .h file, so I cannot modify your file. I don't have the access, or I don't have the permission to modify your files, okay? But I can modify mine all day long, right? So I can say, I want to void do something, for example. Let's try to save this. What is the compiler going to tell us? So it's still complaining about secret being undeclared, but it stopped complaining about do something. Huh, interesting. So what if I say there is an extern int secret? And actually I could also do extern here. It's optional, but yeah, it's good practice. So extern void do something. Somewhere else I know there is a code for a method do something that looks like this. Somewhere else, I know there is a definition of a global variable secret that looks like this. Okay, and this is my code. This is main.c. Okay, go back here. It's compiling. What about if we run it? Well, it looks like it's running, so everything is working okay. The secret is 24, so I was able to call printf and display the value of the variable secret. It was 24. If I call do something, apparently do something is working, doing its job. So do something is able to increment the secret by 1 when it's called. Awesome. So it's awesome for me. It's not awesome for this poor programmer here. He or she wanted absolutely that function do something and that global variable secret to not be accessible by others. And here we are. Now they are. So if I want to prevent that, so I'm putting myself back in the shoes of that other programmer. If I want to prevent that, there's a keyword in C, static, okay? I can add static in front of the declaration of a global variable, in front of the definition, sorry, of a global variable, okay? So in my greetings.c, I can also put it here in front of my function. We're going to see what that does. Static declaration of do something follows non-static declaration. Okay, previous declaration of do something was here. So it tells me I have a prototype here, and that prototype doesn't say anything about static. Okay, well, let me try to fix that this way. I'm going to go ahead and say the prototype should match indeed the definition of the function. And now it's telling me, so it compiles now, okay? So it compiles main.c, compiles greetings.c, everything compiles, but then the linker tells me in function main, undefined reference to secret, undefined reference to do something. So that means that because I protected that global variable with the keyword static and I protected that function with the keyword static, okay, they blocked the linker from actually giving me access, even though I said, yeah, no, somewhere else there is an extern, do something and an extern secret. And the compiler says, sure, okay, then you can use them. But then when the linker put together all the pieces of the code, it realized that these were declared as static, and therefore they were not accessible outside the file in which they were defined. That's what the keyword static does. So that's the last mechanism for our modularity thing. The last mechanism is, hey, look, I can actually protect the things that I don't want other programmers to be able to access by not putting them into the greetings.h. That's the first step. And by defining them as static inside my greetings.c. Okay? All right. Absolutely last detail that is related to this that I'm going to introduce in this video. We use the static here. Well, the word static has another meaning, actually. You can declare a variable inside a function. So, for example, I can have a function here, void counter, display counter. There we go. Display counter. And inside of it, I'm going to declare a local variable, static, int counter equals 0. And then I'm going to do counter plus plus. And I'm going to do printf, the method display counter has been called %d times so far. And I'm going to use counter. So it kind of looks stupid, right? Because I have a method. When I enter the method, I declare a variable, set it to 0, then increment it by 1, so now it's 1. And I'm going to display the method display counter has been called 1 time so far. Sure, why not? But when I call it again, what's going to happen? Well, I would expect counter to be redeclared, set to 0, then incremented, so set to 1, and then the message would say the method display counter has been called 1 times so far. So that would be weird, right? Because every time you call that method, it say, I've been called 1 time so far, I've been called 1 time so far, I've been called 1 time so far. Well, let's see exactly what's happening here. So I'm going to call display counter from the main. Maybe I should clean up a little bit here. So let me clean up all of this. There we go. We're going to do only one thing called display counter, and I want to call it several times. Okay, 3, 4, for example. There we go. Let's go back. Compile. Implicit declaration of display counter. Yes, I forgot. Since I want people to be able to use display counter, I'm going to take this. Here we are, and I'm going to put it as the prototype inside my.h file. There we go. 2 methods and 1 global variable. Save that. Go back here. Whoa, a lot of problems. So this is a syntax error. This is just that semicolon here. Most likely, this is the only problem here. So actually, let's use that as a learning moment, right? Storage class specified for parameter global. So the error is here. But wait, nothing is wrong here. So whenever the compiler tells you I have an error on line 7, that means by the time it reaches line 7, it lost its stuff and it's not able to understand what you're doing anymore. So the error could be anywhere above. And because this is actually in a .h file, right, the error is going to appear in the .h file, but it's going to appear also in every .c file that is including that .h file. So let's go back here. I fix the problem. Let's see if that's enough to make the compiler happy. Compiler is happy. Let's run the code. The method display counter has been called 1 time so far. It's been called 2 times so far, 3 times so far, 4 times so far. So what is going on exactly? If I remove the static keyword, okay, and I try again, so compile, run it, then it does what I expected. So this is how a normal local variable would behave, and this is exactly what we were expecting, okay? But if I make a local variable inside a function, if I make it static, then that means that the first time the function is called, that variable is going to be created, but it's not going to be created in the same area of memory, and that means that it's not going to disappear once the function is done executing, like all of the local variable in function do, okay? Instead, it's going to be preserved. So the first time I call the function, it's like I create a pseudo-global variable, right, named encounter in this file, and I set it to 0. And then I can increment it by 1, I can use it to display, and when I reach the end of my function, this variable still exists. It's not accessible from anywhere else but the function display counter, because I didn't declare it right here, outside of every function. It's only accessible, visible, you would say its scope is only between the curly brace of that function, but it still persists in memory from one call to the next, which allows us the next step, the next time we call display counter, right? We are not going to redeclare the variable counter. We are not going to reinitialize it to 0. This is done only the first time we call the function, but we are going to keep incrementing it, and we are going to keep displaying its new incremented value. So it's like having a global variable to the file greetings.c, but only visible inside the method. So that means I cannot use that variable here, for example, counter equals 0. I cannot use it from anywhere else, any other function in the file, and it persists its value from one call to the other. So generally, yeah, you can use it as, for example, to implement a counter that's going to tell you how many times a given function was called, for example. This is a classic example that we all use. But it's interesting because then it kind of like wraps together the different usages of the keyword static. Okay, so static to protect, to lock into a file, a global variable, or to lock into a file function definition and declaration. But static also can be used to have variables that are going to exist from one call to a method, to a function, to the next call to that same function. And you can keep track of data like that between the calls. Again, that's not a replacement for parameters. Okay, both global variable and static local variable inside functions are not a replacement for properly using parameters. They are just extra features that are available. So that was a lot of material. We are going to wrap it up for this video here on reusable modules. Please feel free, as usual, to use Piazza, forums, whatever we're using this semester in the course to ask your question. Also, come and see me and the TAs during office hours, and we'll be happy to help you out. We are going to use this module organization in our practice exercise during this module, our apprenticeship exercise. And then we're going to also use it in our practice exercise practice assignment, okay? And we are going to keep using this organization throughout the semester. So make sure that you get familiar with it, that you get comfortable with it. All right. As usual, thank you for your attention.